All right. So let's start with hydrogen bonding. We had done hydrogen bonding yesterday, but let's go over it. Let's see the criteria. I told you the three types of intermolecular forces. You have temporary dipole, induced dipole forces, permanent dipole forces, and hydrogen bonding. Collectively, all three are known as van der Waals forces. Yes, the weakest of all these forces is temporary dipole, induced dipole forces, which are found by default in all molecules. But in a non-polar molecule, you will only have temporary dipole, induced dipole forces. Then we have polar molecules. Polar molecules, for example, HCl, HBr, etc. These molecules are polar and they will have permanent dipole forces, which are relatively stronger. If you want to determine the strength of intermolecular forces or the van der Waals forces, specifically which ones, permanent dipole and temporary dipole forces, the strength is directly proportional to number of electrons and surface area. The more the electrons, the more the strength, and the greater the surface area, the greater the strength of intermolecular forces. Why do we study about intermolecular forces? Because there are certain things or certain properties which depend on intermolecular forces, like melting point, boiling point, solubility, volatility, and physical state. We've talked about how melting point, boiling point, volatility, and physical state depends on intermolecular forces. We will see solubility now. Let's now move on to hydrogen bonding. We saw hydrogen bonding was a special case of a permanent dipole forces. Yes, in hydrogen bonded, I told you, all hydrogen bonded molecules will have permanent dipole forces, but not all polar molecules will have hydrogen bonds. There's a special case, it's a special type of hydrogen bonding is a special type of permanent dipole force, and in which two criteria must be met. What are the two criteria? First is you must have a H bonded to an O, or H bonded to an N, or H bonded to an F directly. And the electronegative elements in those bonds, which are O, N, and F, they must have at least one lone pair. If both criteria are fulfilled, then you will have hydrogen bonding. Yes, and this is the strongest type of intermolecular force. Let's see an example of water. Do you see one water molecule with another water molecule? You have H with an O, and you also have oxygen with a lone pair. So you will have hydrogen bonding between the two molecules. How will you show hydrogen bonds? It will be a force of attraction from the partial positive hydrogen of one molecule to the lone pair of the adjacent molecule. Clear? Now, if I ask you that enlist all the types of forces that you see in water, all the intermolecular forces that you have in water. So what will be all the intermolecular forces? Hydrogen bonding, permanent dipole forces, and temporary dipole, induced dipole forces. Which is the strongest type? Permanent hydrogen bonding. Which is the weakest? Temporary dipole, induced dipole forces. Now let's see the second example of hydrogen bonded molecules. Let's see ammonia. Let's see NH3. So we have done the shape of ammonia. It is trigonal pyramidal. Yes. So this right here is ammonia. This right here is another ammonia molecule. So you have ammonia. Now let's see, in here, nitrogen is partial negative, hydrogen is partial positive. So I'm just showing these dipoles right here. Do you have N with an H? Bonded to an H, N bonded to an H? That's the first criteria. The second criteria, the electronegative element must have at least one lone pair. Do you have that? Yes. So which type of bonding can exist between the two? Hydrogen bonding. How will we show this? It will be partial positive hydrogen of one to the lone pair of the adjacent molecule. You can show the hydrogen of this one making bond with the lone pair here, or vice versa. I mean, you can also show it from this to this. Either or is fine. So you see ammonia also shows hydrogen bonding. Let's see the third example. Let's see HF with another HF molecule. Now right here, hydrogen is partial positive, fluorine is partial negative, partial positive, partial negative. Let's see, fluorine it's in group 7, so it has 7 outer electrons. One is making a bond. This is the second, third, fourth, fifth, sixth, and seventh. Do you see you have 3 lone pairs? Yes. I'm just going to put the lone pair here and the partial negative there. So, yes. And right here, You have a lone pair, and you have, do you see this is a polar molecule right here? The first criteria, F with an H, is that fulfilled? Yes. The electronegative element must have at least one lone pair. Does it have it? Yes. So can this show hydrogen bonding? Yes. And how will you show it? It will be a force of attraction between the partial positive hydrogen to the lone pair of the adjacent molecule. So this right here is hydrogen bonding. Yes. Clear? Now, so hydrogen bonding can be seen in water, ammonia, HF. Yeah. Moving on. Explain why ammonia is soluble in water using a diagram. Now, remember I told you that the properties like solubility, volatility, melting point, boiling point, they all depend on intermolecular forces. So we studied about how melting point, boiling point depend on intermolecular forces. Now let's see how solubility depends on it. So solubility means something dissolving in water. And you can see water makes which type of bonds? Hydrogen bonds. Yeah. So if anything that can make hydrogen bonding, it will be soluble in water. Now you'll be like, but miss, NaCl is soluble in water. That does not make hydrogen bond. By hydrogen, now you see hydrogen bonding is an intermolecular force. And intermolecular forces will exist between molecules, and molecules will be of covalent compounds. So please don't involve ionic bonding here. Don't say, oh, NaCl does not have hydrogen bonding, but it is soluble, because that's not covalent, that's ionic, that's separate, right? But right here, do you see all the intermolecular forces that we have done? We have done it with covalent bonded structures, because molecules exist because of covalent bonding. Clear? Now, anything that has hydrogen bonding will be soluble in water. So they're saying, explain why ammonia is soluble in water using a diagram. So ammonia is soluble in water because ammonia can make hydrogen bonds with water. And now you need to show that, diagrammatically represent it. So you will make ammonia, that's NH3, right here, and you have water. Water is H2O, right here. So you have ammonia and water. And this can dissolve. Why? Because it can make hydrogen bonds. You need to show the hydrogen bonds. So this is partial negative. This is partial positive, partial positive, partial negative. How will we show hydrogen bonds? Lone pair of one molecule to the adjacent molecules, partial positive, right? So either you can show it from this guy to this guy, or from this to this, either or. So let's show the hydrogen bonds right here. Intermolecular force between the partial positive hydrogen of one molecule to the lone pair of the adjacent molecule. Clear? Explain why ethanol is soluble in water. Again, can you guys try this now? Why is ethanol soluble in water? Why is ethanol soluble in water? Now again, if it is soluble, that means ethanol can make hydrogen bonds with water. And let's see the hydrogen bonds. So you have ethanol, which is C2H5OH. So you have C2H5OH. This right here is ethanol. Let me make water right here, H2O. Water has two lone pairs. Oxygen here has two lone pairs as well, because oxygen is in group 16. So you have two lone pairs over here. This side is partial negative. This side is partial positive, partial negative, partial positive. You can show hydrogen bonding from this H plus to the lone pair of the adjacent molecule, or you can show it from this lone pair to the adjacent H plus, like this. This is hydrogen bonding. And because it can make hydrogen bonds, it will be soluble in water. Clear? You can show either or. You can show both, you can show either or. Explain why HF has the highest boiling point compared to HCl, HBr, and HI, which are called hydrogen halides. So they are saying HF has a higher boiling point compared to HCl, HBr, HI. Why is that? What does HF have? It has hydrogen bonds. Yes? So this shows hydrogen bonding. What about the rest of them? What about these? They show permanent dipole forces. Yes? So these have permanent dipole forces, whereas HF has hydrogen bonding. Which is the strongest intermolecular force? Hydrogen bonding. Therefore, HF will have a higher boiling point. So HF shows hydrogen bonding, which is the strongest intermolecular force. Yes? So it is the strongest intermolecular force, hence more energy is required to overcome these forces. So more energy is required to overcome the strong forces, hence highest boiling point. And what about the rest of them? HCl, HBr, HI, what do they have? They have what? Permanent dipole forces, which are relatively weaker. Therefore, they have, the boiling point is low. Is that clear? Now, between HCl, HBr, and HI, between these three, which will have the highest boiling point? HCl, HBr, or HI, which will have the highest boiling point? HI. Why? Because this will have stronger permanent dipole forces because of more number of electrons. We did this yesterday. The more the number of electrons, the greater the boiling point. Yeah. So the highest would be HF, followed by HI, followed by HBr, and the lowest boiling point will be of HCl. Yes? And why would HI be the why would HF be the highest? Because of hydrogen bonding. And what about the rest of them? They all have permanent dipole forces, but HI has the most number of electrons. Clear? Is this clear? Now, let's move on to the next part of this, the last part of this chapter actually. Let's move on to polar covalent bonds. Now you see, covalent bonds are made up of atoms sharing their electrons. And what about ionic bonds? Ionic bonds are formed between ions, oppositely charged ions. Now there is a little bit of covalent character in ionic bonds, and there is a little bit of ionic character in covalent bonds. Let's see what we mean by that. So let's see polar covalent bonds. What are polar covalent bonds? These are those bonds which are formed between atoms with different electronegativities. Yeah. So we call such bonds polar. So let's see an example of a polar covalent bond. Let's take CCl. Let's take CBr. Let's take Ci. Let's take O with an H. Let's take N with an H. Let's take C with an N. Yes? Let's take these bonds. Do you see that in these bonds, this side is partial positive, partial negative, partial positive, partial negative, partial positive, partial negative, partial negative, partial positive, partial negative, partial positive, partial positive, partial negative, based on the difference in electronegativities. Do you see? These bonds are made up of atoms, but they still have partial charges on them. So can I say, even though these bonds are covalent, but they do look a little like ionic compounds? Yes, or ionic bonds. So can we call this ionic character in a covalent bond? Can we say that? Yes, because you have, just like ionic compounds where you have ions, these guys also kind of look like ions. Not completely, not entirely, partially, but yes, that's why we call it an ionic character in covalent bonds. Clear? Now the reverse is also possible. There in ionic bonds, you see what? Covalent character. All right. Now, if you remember, we did AlCl3, and we studied the shape of AlCl3. What was the shape of AlCl3? Trigonal, planar, sp2 hybridized. And if you remember, I made AlCl3 covalent. Even though it is made up of aluminum, aluminum is a metal. Chlorine is a non-metal. Between a metal and a non-metal, you should have which type of bonding? Ionic. But still, we made AlCl3 what? Covalent. Why? Let's see. Now, let me take ionic bonds. Now, this concept you need to understand very clearly because this will go with you in A2 as well. All right? So just listen now. Stop writing. All right? Because there are a few things happening step by step, so you need to follow. So let me take examples of NaCl, MgCl2, AlCl3, where I know NaCl is ionic, MgCl2 is ionic, but AlCl3 we did was covalent. And why is that? Let's see. So you have NaCl. Now let me take Na plus Cl minus, Mg2 plus Cl minus, Al3 plus Cl minus. Yeah. So I've taken these ions based on their radii. You know, across the period, the radius decreases. Yes. So we know, sorry, across the period, the radius decreases. Yes. For the cations, right here, this will be Na plus, this will be Mg2 plus, this will be Al3 plus, right? And this right here is an anion, Cl minus, Cl minus, Cl minus. Clear? I've drawn these. Now we know that these guys are ionic. This is also ionic. And we know this guy right here is covalent. Why so? Shouldn't it be ionic? Let's see. There is something called charge density. Something called charge density. What is charge density? Charge density is basically charge per unit area. An area we can define on the basis of radius. So can I say charge density is directly proportional to charge and inversely proportional to the radius. The more the charge, the greater the charge density. The lesser the radius, the greater the charge density. It is basically the charge spread over the entire area. An area can be given in terms of radius. So it is charge upon radius. The greater the area or greater the radius, there will be less charge per unit area then. Yeah. So that's why we say it is directly proportional to charge, inversely proportional to the radius. Now, if you look here, we know this right here is our cation and this right here is our anion. Charge density is a property of cations. It is a property of who? The cations. Now, based on this, which one do you think, which cation has a higher charge density? Sodium, magnesium, or aluminum? Aluminum. You all understand that because aluminum has a greater charge, smaller radius. And why does it have a smaller radius? Because across the period, the radius decreases. So can I say this has a higher charge density? This has a lower charge density. Clear? There comes the next thing now, which is the polarizing power. Polarizing power is directly proportional to the charge density. So there is something called polarizing power, which is directly proportional to the charge density. The more the charge density, the more the polarizing power. What do you mean by the polarizing power? Polarizing power is basically the ability of the cation to pull the electrons of the anion. So it is the ability of the cation to pull the electrons of the anion towards itself. And it is directly proportional to what? Charge density. So the one which has more charge density, can I say has more polarizing power? Yeah, because they're directly proportional. More charge density, more polarizing power. So can I say based on this, this has high polarizing power, this has low polarizing power. Clear? Then comes the third thing, which is the distortion of the anion. So the distortion of the anion is directly proportional to the polarizing power. The more the polarizing power, the greater will be the distortion of the anion. Because polarizing power is what? Ability to pull the electrons of the anion. So which one has more polarizing power here? Aluminum. So it will pull the electrons of the anion. Can I show it like that? Can I say this is aluminum pulling the electrons of chloride? This will have a higher polarizing power, therefore more distortion. This has lower polarizing power, therefore less distortion. And this has the least polarizing power, therefore the least distortion. Clear? So we have charge density, which is directly proportional to charge, inversely proportional to radius. Based on that, aluminum has the highest charge density. Then we have polarizing power, which is directly proportional to charge density. Based on that, aluminum has the highest polarizing power. What is polarizing power? Ability of the cation to pull the electrons of the anion. So you see, the more the polarizing power, the more will be the distortion of the anion. And you can see aluminum is distorting the anion because it's pulling the electrons really strongly. Clear? Because of high polarizing power. Now, the more the distortion, more will be the covalent character. So covalent character is directly proportional to the distortion of the anion. Because when they pull the electrons, they end up pulling them so strongly that they end up sharing the electrons. And sharing electrons is what phenomena? Covalent. So you see, because aluminum has a smaller radius, greater charge, it has high charge density. Because of that, it has high polarizing power. Because of that, it will pull the electrons of the anion very, very strongly, distorting it. Because it distorts it so much, it literally pulls the electrons and they end up sharing the electrons, giving you a covalent compound rather than ionic. Now you'll be like, Miss, wow, like does it only depend on aluminum? Like it's just pulling and the chloride is just sitting there giving away its electrons. Considering chloride is electronegative, chlorine is electronegative, shouldn't it retain its electrons or whatsoever? But what is happening? Like aluminum just pulls it and then we're done. It's a covalent all of a sudden. No, it's not just dependent on the cation. It depends on the anion as well. If the cation is willing to pull, or it can pull the electrons, the cation should be able to pull, the anion should be ready to give. All right. So it depends on both. It depends on the cation as well as on the anion. So let's see. Can I say that this right here has more covalent character? Because you see more distortion. And can I say this has less covalent character because there is less distortion? Yeah. For you to have covalent character, or for you to have covalent bonds, so to have covalent character in ionic bond, I told you it just doesn't depend on one guy, it depends on both. It depends on the cation and the anion. Cation should be able to pull the electrons, and to be able to pull, it should have high polarizing power, and for that it should have high charge density, and for that it should have high charge and less radius. Yes, so cation, in order to pull the electrons, must have high polarizing power, which is if it has high charge density, which is if it has more charge and less radius. But I told you, it just doesn't depend on one guy. It also depends on the anion. It should be willing to give the electrons. And that property is called polarizability. What is it called? Polarizability. The cation should have a high polarizing power to be able to pull the electrons, and the anion should have high polarizability, that yeah, you can come take my electrons, I want to get polarized. So that is called polarizability. So the cation should have high polarizing power, and the anion should have high polarizability. That means it should be wanting or willing to give its electrons. And this polarizability depends directly on the charge and directly on the radius. So it is directly proportional to charge and directly proportional to the radius. The more the charge, more the polarizability. The more the radius, more the polarizability. And if the cation has high polarizing power, and if the anion has high polarizability, they will end up making what? Covalent bonds instead of ionic, because the cation wants to pull and the anion wants to push the electrons. So that means they will end up sharing the electrons, giving you an covalent bond, not an ionic bond. Clear? So we know that, let's see, when will you have a covalent character in ionic bond? If the cation has high polarizing power and a high charge density. And for that, what do we need? We need more charge and we need smaller radius. Clear? And what should the anion have? The anion should have high polarizability. And for that, what do we need? We need high charge and greater radius. If cation has high polarizing power, anion has high polarizability, the bond will be covalent. Clear? Now let's see an example of AlCl3. So you know Al3 plus Cl minus. This gives you AlCl3. And let's see the example of Al2O3, which is aluminum oxide. Here you have Al3 plus O2 minus. Now you see, here the cations are the same. For both of these, the cations are aluminum ions. And here also the cation is this, and here also the cation is this. So cation is the same. So can I say the polarizing power for both is the same? Now let's check the anion. Chlorine is in period 3. Oxygen is in period 2. Yes? You know, this is right here oxygen, this is right here chlorine. Which will have a greater radius? Chlorine or oxygen? Chlorine, because it is in period 3. Period 3 means how many shells? 3 shells. Period 2 means how many shells? 2 shells. So this has 2 shells, this has 3 shells. Which has a greater radius? Cl. So Cl has a higher radius or a greater radius. So that means, can I say this has a higher polarizability? Yes. So this will allow aluminum to pull its electrons as opposed to oxygen, which will not allow. Why? Because oxygen or the oxide ion has low polarizability. Why? Because it has smaller radius. Yes. So because this is pulling the electrons and Cl is allowing that pull, what type of bond will you have here? You will have a covalent bond. What type of bond will we have here? This will remain ionic bond. Do you understand that? So can I say that AlCl3 is a covalent compound? And why is that? Because aluminum ion has high polarizing power and chloride ion has high polarizability. On the other hand, you have aluminum oxide. Aluminum oxide is an ionic compound. And why is that? Because aluminum has high polarizing power, yes, but oxygen has low polarizability. So they remain ionic. Clear? If you remember from O levels that anything which is covalent or any compound which is covalent, it will be acidic. Do you remember covalent compounds are acidic and ionic compounds are basic? So if you don't, you can just know right now, covalent compounds are acidic in nature. So this will be acidic in nature. This is ionic, therefore this will be alkaline or basic. Yes? And is why, if you remember, we used to say aluminum is amphoteric. What is amphoteric? Behaves as acid and alkali. Do you see why? Because its chloride is acidic and its oxide is basic. Is why we say aluminum is amphoteric. So aluminum is amphoteric because of covalent chloride and alkaline or basic oxide. So aluminum is therefore amphoteric due to a covalent or acidic chloride and basic or ionic oxide. Now, very frequently they ask you, which of the following is most likely to make a covalent compound? And your options are metals. And they put aluminum as an option. Without thinking twice, you need to take on aluminum because aluminum is most likely to make covalent compounds. The other option is beryllium. We'll just see that. But they will never give both of them as an option. All right. So they'll either give aluminum or they'll either give beryllium. And we'll just see beryllium. It has similar properties to aluminum. It is in group 2. All right. So let's see. Is this clear? Is this clear? Now let's see properties of beryllium. So beryllium behaves the same way as aluminum. Let's see beryllium. Beryllium is in group 2. So that means it will have a charge of 2+. Now beryllium 2+ has a high charge and a smaller radius. Therefore, it has high charge density. And therefore, it has high polarizing power, just like aluminum. Is why when we do group 2 as a topic, separate topic, as a separate chapter, you'll see we don't consider beryllium as part of group 2. Why? Because it behaves like a group 13 or aluminum. It behaves like aluminum. So we don't even consider this to be part of group 2. It is in group 2, but we don't really consider its properties to be similar to that of group 2 elements. So right here, it behaves like aluminum. So can I say beryllium chloride will be covalent, just like aluminum chloride, and beryllium oxide will be ionic. So since this is covalent, can I say this is acidic? Since this is ionic, can I say this is basic? Can I also say beryllium will be what? Amphoteric, because it has a covalent chloride and a basic alkaline oxide. Is that clear? And again, why? Because it has a higher charge density. More charge, smaller radius, therefore more charge density, more polarizing power. So just like aluminum, this will behave the same way. Is this clear? Is this clear? So if they ask you which element is most likely to make a covalent compound, you will say aluminum. If that's not an option, then your answer will be beryllium. And it's why, if you remember, we've done BeCl2. Where did we do it? Shapes of molecules. What was the shape of BeCl2? Linear, 180. Do you remember that? And it was covalent. Even though beryllium is a metal and chlorine is a non-metal, but they still make covalent compounds. Why? Because of more polarizing power of beryllium and high polarizability of chloride, making the compound covalent. Clear? Do you all understand this? Any questions?